This mini Centurion is going to be on display at VCF Southwest coming up real soon, and in order to make sure that the machine was in tip-top shape for that event, we had 3 large hurdles that we had to overcome. The first was the aesthetics. We needed to put a new top on it, new front wood panels down here, and new metal side panels. And I think we absolutely nailed it. It looks like a genuine Centurion from the 1970s. It looks perfect. The second hurdle that we had to overcome was the hard drive. This is a CDC built Hawk drive, has 5 megabytes fixed, 5 megabytes removable, and in the previous episode, we got it so very close. The removable platter is working, we are booting into the operating system, and I think that'll be perfect for the event. The third and final hurdle that we have to overcome is this data terminal on top. This is an ADS Regent 200, and it works fine as a data terminal, except that at any speeds above 4800 baud, the screen flickers every time you try to scroll, and that's just not going to cut it for a machine that's going to be on display that people are going to get hands-on with. So we need to dive in deep because I think it might have a firmware bug in it. So that is what we're going to be working on today, except before we get into that, I have a pretty funny story for y'all. Remember this CDC Hawk drive that we got going in the previous episode? Well, hilariously enough, it's broken again. I mean, isn't that hilarious? I mean, so what's going on here? And actually, if this is your first episode in the Centurion series, unfortunately, it's a direct continuation of last week's episode, which is a direct continuation of the 48 episodes in the series that precede it. So you might be a little lost. It's a bit like walking into Avengers Endgame and going, who's the man in the iron suit? But I'll try to sprinkle in enough information so that you're not completely in the dark. Also, in last week's episode, there was a ton of amazing comments, but I think the way that I summed things up in it might not have been all that lucid. I was a little tired and I edited that video in an airport. So if you were confused about how things went down in last week's episode, hopefully I can clear that up for you right now. I'm going to try and address a lot of the confusion that people were writing in the comments. And essentially what happened is this is a CDC Hawk drive. You have a 5 megabyte fixed platter and a 5 megabyte removable platter. And we were actually able to spin the drive up, float the heads, and read the data off of both platters. We were able to boot fully into the operating system that's stored on the removable platter, and we were even actually able to read the data off of the fixed platter. We read every single sector perfectly except for the first like 8 to 10 sectors that are the initial program loader. But off camera, I went back and tried to read those sectors again, and I actually got clean reads out of them. I still think that that track is aligned slightly differently than the rest of the platter, but it doesn't matter because we were able to combine those 2 reads together on the laptop, and now we have a perfect image of the fixed platter, and we've been digging around in it in the emulator, and it's everything we hoped it would be. However, whenever we tried to write to the fixed platter, it would fail. We would get a disk fail error, and I even tried going into a memory monitor and poking the MMIO addresses of the disk controller cards directly. And when I tried to do a format sector, the memory monitor spits back the Hawk status register with a big fat error, and the fault light on the Hawk itself lights up. That tells me that we have a bad head. I even went so far as to swap the plugs on the card inside the card cage of the Hawk so that the lower head on the fixed platter was then plugged into the removable platter. We ran the same test. The fault followed the head. So we have a bad head, but how can we have a bad head and still read all of the data off of the fixed platter? Well, the way that the heads are designed is that the coils come out in a star pattern. You have voltage coming into a center point and then 3 coils coming out from there. You have a read coil, a write coil, and an erase coil. And then those coils go to control transistors that turn on or off depending on which coil we're trying to control. So the write coil and erase coil could both be bad and the read coil won't care at all. So I think that's what's going on here. We have 1 or 2 bad coils within that head that allow it to only ever read data. We can't write any data with that coil, which means that our fixed platter is essentially a read-only platter, only it's got some weird alignment issues on it. And while we were testing, we blew a couple of holes in some sectors to try and get that testing done. So we can't rely on the fixed platter as being a read-only platter that our operating system is on. We need to actually get some real data onto that and boot from it. But if we think about what we want to be a read-only platter, it's the removable platter that we really want to be read-only, because that is our backup disk. We don't want to accidentally destroy the data on it and not be able to successfully back up to the fixed platter if something goes wrong. And I think our removable platter heads are totally fine. So here's what I'm thinking. We're going to remove the lower head on the removable platter and put it on the lower position of the fixed platter, and then take the read-only broken head from the fixed platter and put it on the removable platter. This will make our removable disk totally read-only. We can never write anything to it, but we should be able to read and write to our fixed disk, which means that we can run all sorts of interesting programs. And for the Centurion, 5 megabytes is plenty of space. So that's what we're gonna do first with this. Oh, I didn't answer why it was broken. The bump stops that I put in were way too stiff, or I didn't get the clamp bolts on the heads too tight, and so turning the drive on and off has caused the heads to shift out of alignment again. So we got to do a head alignment anyways, which means I'm going to be in there messing around with the heads. I might as well swap those two lower heads and see if we can get the fixed platter to actually be a read-write platter, because I never had any intention of writing to the removable platter anyways. So let's get to work. I'm gonna speed run this one because honestly, this video is supposed to be about the data terminal, and here we are elbow deep in a hard drive again. There's a couple of things to note while I do this. The Hawk is set up for hard sectoring on the Centurion, which means that as soon as I pull the fixed platter out like this, the relationship between the data on the platter and the sector plate on the bottom of the drive is lost. So the data on the platter can no longer be recovered, which is fine because we successfully backed up the entire platter in the previous episode. We've been digging through it in the emulator and it works excellently. So if we ever need anything specific off of this platter, we have it. Working with the heads is a fiddly affair, and I'm trying to be as gentle as possible here so as not to damage them. And the heads are actually probably the rarest and most difficult to find part in these entire drives. The platters can be replaced using any removable pack platter from a multitude of drives, including DEC RL packs. So there's a ton of good platters still out there. But heads, those are specific to CDC 9427H drives. Furthermore, there's different variations for 200 tracks per inch and 400 tracks per inch, as well as pre-erase and straddle erase, so finding appropriate heads is near impossible these days. I do have a few heads that have blown coils, and some days when I get my hands on a proper microscope, we may take a swing at rewinding the core in these heads. Looking at these macro shots, you can see it might just be possible. At any rate, once I've got the drive buttoned back up, I want to take care of the rubber bump stops. The ones from last week's episodes were a bit too stiff, so we'll try a different type of rubber. Unfortunately, the velocity transducer is still stuck in place even after removing the set screw, so back to just being careful. The new rubber pads may be too stiff as well, but we'll give them a shot. This is probably the easiest internal part to access and change, so if it gives us grief in the future, we'll keep trying different stuff until we find the right combo. With everything back together, I let the drive spin purge for another hour or so, then spun it up and let the heads automatically load. Nothing sounded horrific, so let's do a head alignment. The removable platter put up a fight though. Just like the fixed platter in the previous episode, track 0 seemed to have a slightly different alignment than the rest of the platter. I ended up having to align the heads with them positioned at track 0, which you're not supposed to be able to do. But a screwdriver covered in tape and some very careful positioning, and I managed to get it done. After seeking around to a bunch of different tracks, it seems that this platter is now aligned perfectly. It's all back together, heads are loaded, everything sounds good. Now we have the lower heads swapped around, so let's see if we can write anything to the fixed platter, and we can actually do that within the memory monitor. So that's what we're sitting in here. If we do MF140, this is going to tell it what platter we're selecting, and we want to select drive 1 platter 1, so 0, 1 here. And then we want to do, let's do MF141. This is going to tell it where we want to write something on that. And we'll just pick something way out in the middle of no man's land, like 2000 here. And then we will do MF143. And we're going to set this to 02. And that's telling it that drive 1, platter 1 is going to have the write bit mask on, which is essentially a software write protect. Now we want to actually command the drive. So we do MF148, 03 is an RTZ. Yeah, did that. MF148, 02 is a seek. MF148, 05 is step 1 of a format. MF148, 06, I've got that backwards. MF148, 06 is step 1. MF148, 05 is step 2. That should do a format write on that sector. So if we do MF148, 00, that is a read. Then MF144, that's our status, 0070. That means all good, and that we have write enable on cylinder, and drive ready. Perfect writes and readbacks of formatted sectors on that platter with the lower head. So we now have a fixed platter that we can read and write from. And well, when I was aligning the heads, I aligned them on the removable platter. So we have a read-only removable platter and a read-write fixed platter, which was what our goal was. That is excellent. So now that we've got that going, let's get into the operating system. We'll hit the load opsys button. We're at D equals, let's do H0, 3 RTZs, that's excellent news already. We want to do S equals 0. Go ahead and hit enter on that. We'll do 082489. And as soon as it says exec ready, we are fully in the operating system. So if I do a .sta, we can see our 2 disks here. Disk 0 is the removable platter, that is system. Disk 1, that's all stars, is our now fixed platter that we need to format and put something down on. The problem is that every time I try to do a new disk on that platter, it fails. So if I do s.newDisk1, it's still failing. That was the exact same problem we had last time. But I think something different is going on here. Let's try something. We'll cancel out of this. We'll do a Control C, do a con, and then we'll do .noguard1. This is just going to try and flip some bits that are on that platter. Boy, it's very upset about that. Okay, so disk fail at 000E, that's the location, the sector that it's trying to write, and then 2030. And if I look up the Hawk status here, 20 is going to be a sector address error, and then 30 is write enable on cylinder drive ready. So the drive is actually working totally fine. It's just not finding any bits there, which we know. Of course there's no bits there. We pulled the platter out and put it back in. That sector's wrecked. So what we need to do is we need to format the entire platter so that we can have a known good starting point to go through and start flipping bits. Now, in every iteration of Centurion operating system in perpetuity, there's always been a .format command. So if I do .format1, I get a JX 0-CTL statement error. That means that the .format command doesn't exist on this copy of the operating system. And that is very strange. It absolutely should exist. And without the .format command, that puts us in an interesting place. We can't format a platter and then copy new data to it. So I think what happened here is that the dealer in Cincinnati, where this drive and operating system originally came from, actually dug through the operating system files and deleted the .format command, so customers would be forced to buy pre-formatted disk packs from the dealer. They couldn't get third-party disk packs, format them themselves, and go from there. So, well, that dealer doesn't exist anymore, and we can't buy pre-formatted disk packs, so we gotta come up with some way to come around this. And I think the only way to do that is for us to essentially write a new format program that runs from the d equals prompt, and that's going to take a little while. So instead, I'm going to shift focus now that I know that the drive is fully working, and all we need is a little bit more software development, and then we can get that drive up and going. So I'm going to shift focus to the terminal, which is still flickering. So if I do a .dir 0, bam, every time the screen tries to scroll, it flickers. So what I need to do, I think, is spin the mini Centurion down, get the data terminal hooked up probably to my laptop so I can reliably spew some data at it, and then open it up and see if we can figure out why it's doing this, and hopefully we can find some solution. So, well, more work to do. All right, let's get to the original purpose of this episode, the ads Regent 200 data terminal. Because RS-232 is awesome, I can do ridiculous stuff like hook a USB to RS-232 cable into a breakout box that I'm using to create a null modem cable, and then hook that into a DE9 to DB25 converter. But that means I can now hook my modern Asus laptop up to my 1970s ads terminal. We'll flip the power switch on, open up TerraTerm on the laptop, and press some keys. And sure enough, they're being displayed over on the terminal. That's excellent. I can use this to stress test the terminal by just pasting a large block of text and having TerraTerm send it at full speed across the 9600 baud connection between the two. And there we go. We can see the screen is flickering like crazy. Let's get a comparison going on. This is the ads Regent 100 data terminal I normally use on the big boy Centurion, and on it, perfectly smooth scrolling. If we look at the two side by side, all I'm doing here is unplugging the cable from one and plugging it into the other. And yeah, that Regent 200 is unhappy for sure. So let's crack both of these open and take a look inside. Fortunately, they're both pretty dead simple to get into. 4 screws hold the top in place, then 4 more screws let you get the CRT cage out of the way. 16 screws in total, and we're in. Now that I've got them apart, it's really fascinating to look at the differences between them. As far as I can tell, the board artwork is identical between the two. All of the ICs, all of the passives, they're all in exactly the same place. The only difference that I can see is how the keyboard plugs into the main board. On the Regent 100 here, it's using these kind of weird flat cables, and on the Regent 200, it's a more traditional ribbon cable. But you can still see the footprint for the flat cable connector next to it. So this looks like it was just a minor update to go to a more conventional ribbon cable. The Regent 200 also has an additional ROM, presumably for all of the added functionality of the keyboard here. The Regent 100 doesn't have that ROM, but it does have the footprint for it on the PCB. There's also an unpopulated socket on the Regent 100 that is populated on the Regent 200, but I don't think that's where the problem is. On the Regent 200 here, I already went through and checked all the voltage levels and looked for ripple and all of that, and it's totally fine. So that means that the failure is somewhere on the PCB itself, and a lot of people have suggested that it was a firmware bug. I even have some people that I talked to that remember using the ads Regent 100 and 200s back in the day, and that they did have a firmware bug above 4800 baud. That's exactly the type of failure that I'm running into here. And so I think we might be able to determine that by doing a little bit of ROM swapping. The ROMs in the Regent 100 we know are good because it scrolls totally fine. And so these may have the updated code that get rid of that bug. Now I've already gone through and backed up all of the ROMs on the Regent 100, so I'm not too worried about blitzing them. It would be unfortunate, but we can get around it if we do. So I think what I'm gonna do is I'm gonna pop these ROMs out and I'm gonna put them into the Regent 200, fire it back up, and see if that solves our problem. I have absolutely zero idea how this is gonna go, but there's really only one way to find out, and that's to flip the power switch. So it beeped once. It never beeped again. Usually it beeps a second time. Let's let the CRT warm up. Maybe we'll see an image on it. We do have a flashing cursor. We don't have our status bar on the bottom here. That's interesting. Not how I was expecting this to go. And yeah, we're not sending or receiving any data at all between the two. I tried every combination of ROM imaginable between the two, and they're just different enough that it's never going to work. The only ROMs that were identical were the topmost. These are the same between the two apparently, but all the other ROMs are just different enough that this one never actually even successfully booted. So we have a firmware bug, but without knowing what the disassembly of the raw hexadecimal on those ROMs is, and without knowing the schematics of the board, it's going to be really tough to try and hunt down that firmware bug and come up with a solution. So I don't think we can actually fix this terminal to run at 9600 baud without flickering. However, check this out. If I come over here and I hit enter on my laptop, it's going to start sending data to the terminal. And yeah, you can see that data is scrolling by just fine. At any speed from 4800 baud and below, this terminal works exactly like expected with no flickering. So if we want to use this terminal with the Centurion, we just need to set it to 4800 baud, right? Well, it's not that easy. The Centurion baud rate is programmatically changeable, which means that you can just run a little script within the operating system and it changes the baud rate of whatever port you're working on. But the default for port 0, which is the console port, is 9600 7E1. You cannot change that physically on the card. It will always be 9600 every time you turn the machine on. So if we wanted to use 4800 baud, we'd have to do something stupid like boot with 9600 baud, go into the operating system, change to 4800 baud, change the setting on our terminal, turn the terminal off and on again, and then we could use it at 4800. That's a royal pain. I don't want to do that. So I'm going to take a look at the MUX card and see if we can figure out a way to force it to be 4800 all the time for port 0. Now that is a dumb solution. The smart solution would be to just use a different terminal, but I really like this terminal. This Regent 200 was on loan from the guys up at VCF East who are absolute legends, and it's a gorgeous terminal, and I want to have this on that machine and use it with it. So I think that might be a good stopgap until we can figure out how to update the firmware on this to handle faster baud rates. This is the MUX card, and it handles input-output to 4 serial data terminals or even a serial printer. And I mean, it's fairly obvious because we have the 4 ports here on the end, but also we've got the 4 large UARTs right here. Now there's a couple different revisions of this MUX board, and they all use slightly different UART chips. These are COM 2017s, but the high resolution photos that I have actually have Intersil IM6402s on them. These are all pin compatible, so it doesn't really matter which datasheet we're looking at for which one. And the IM6402 or the COM 2017 here, you can see it is a 40 pin UART, and it has some pretty interesting features, but the pin that we care about the most is going to be pin 17 here. This says the receiver register clock is 16 times the receiver data rate. And this is for receive, and if we look at the next page here, pin 40 is the transmitter register clock. So these two are probably going to be tied together, and that's where the clock signal is coming in. And if we look at this little excerpt of the schematic that I have down here, this schematic of the MUX card was fully reverse engineered by Meisaka. She did an absolutely stunning job, unbelievable work here. And because of that, we're going to be able to do some pretty tricky stuff. But if we look at pin 17 and 40 here, they're tied together, and they go over to a 74LS151. And if we look at the data sheet for that LS151, we can see it's an 8 input multiplexer. So what this means is that you have 8 different inputs coming in, and depending on what your 3 selection bits are, S0, 1, or 2, you are selecting what the output is. Now S0, S1, and S2 all go over to this 74LS75, which is how we're programmatically selecting which input is making it to the output. Now these 8 inputs all go down to a clock divider that's taking the overall clock from the crystal and dividing it down into multiple options. So we're just picking which of those divided clocks makes it through to the output. And so all we really need to do is cut S0, S1, and S2 off from the LS75 and control them separately ourselves. And then we can set it to 4800 baud, and regardless of what we set programmatically, the MUX card will always be doing 4800 baud, which will work perfectly with that terminal. I've said it before and I'll say it again, this Radio Shack desoldering iron rocks the house. It's so good that the prospect of desoldering ICs doesn't scare me at all anymore. Just suck all the solder out, use the regular iron to break the pins free from the through-hole barrel, then give it a little pry with a hook tool and the IC comes right out, leaving clean through holes and traces behind. Now I want to build something that plugs into a socket, and I have these awesome round machined female pin headers, but I don't have the corresponding male headers that go with them. So I'm just going to make male headers by soldering solid core wire into some of the female headers. It's a bit fiddly and decidedly not the right way to do it, but it's what I had on hand and should work just fine. With the extension lead soldered in place, I can just slip it into the perf board and solder it down nice and tight. I just need to rinse and repeat, and now I have two perfectly spaced dip male headers. Now I want to solder the female headers to receive the original IC, and all the pins except for 3 will pass straight through. The 3 that won't are the address pins. This is the schematic for how I'm going to build this little daughter board. It's pretty dead simple, but allows me to physically select the address going into the LS151. The resistors are pull-ups to 5 volts, and the dip switch will ground the input if on. And speaking of dip switches, let's get our 3-position switch installed. That turned out really compact and decently nice looking. It was a pain to solder up all the pass-through connections because it was so tight. Someday in the future I may remake the board and cut a proper PCB, but for now that looks like it's going to work like gangbusters. Let's get a socket back into the MUX board itself. I'll just use more of these round machined pin headers, and after soldering them in place, the daughter board just presses right on down. That looks awesome. It also looks period correct and almost kind of original. The best part is the MUX board itself is completely unmodified except for adding a socket, and I wouldn't really consider sockets to be modifications. At any point I can pop the daughter board out, move the LS151 down to the MUX board, and we're back to 100% original functionality. No cut traces, no lifted pins, just a super simple add-on board. I took my best educated guess on how to set the dip switch there, but I have no clue if it's correct. But I do know a quick way to test it, and that's just to turn it on. If the screen clears and we get a D equals prompt, that means that everything is working because the terminal is set to 4800 baud. So here goes nothing. Oh, that's close. I definitely have a baud rate set wrong, but the fact that we're actually getting something out of the port is good-ish. Turns out I had a slight wiring problem on my little breakout board here, but I fixed that now. So I've got the scope on the clock signal going into the UART chip here, and if we're going to be at 4800 baud, we want to do 4800 times 16. We want to be at 76.8 kilohertz. And right now the dip switch looks like it's at 4.8 kilohertz. So let's see if we can make this go faster. Ooh, that is considerably faster. Looks like we're up to 20 kilohertz. That's going to be a lot faster. That's 307 kilohertz. We need somewhere in the middle here. 76.776 kilohertz. That is perfect. So that's the setting that we need. That should be 4800 baud. Everything's all plugged in. The MUX card looks like it's at the correct baud rate, and the CRT is still set to 4800, so let's flip the power switch. Yeah, the screen cleared and we got D equals. Can I type? H0, H1, it is working perfectly. That was the most hacky hardware solution to a software problem I've seen in a while. Last thing to check is to hop into the operating system and see if we can do a directory listing without the screen blinking at us. So we'll do H0, did 3 RTZs, DOS 5.6, we want to do S equals 0 here. We'll hit enter. Our date is 08/24/89. Exec ready, we're fully into the operating system. We'll do a .sta for a status. No blinking so far. We'll do a .dir 0. And look at that. Scrolling perfectly, no blinking, no flashing. Yes, it was a very hacky way that we achieved this, but we actually achieved it, and it's gonna be perfect for VCF Southwest. Now, I know what you guys are thinking. Did I check everything to make sure at 100% that this terminal would not function at 9600 baud without flickering? Most notably, did I check flow control? And of course I checked flow control. The benefit of using TerraTerm plugged directly into a terminal to test it is that you can check things like CTS and RTS or DSR and DTR and stuff like that. And I checked it all, and the behavior was identical no matter what. It always flickered at 9600 baud, but it never flickered at 4800 baud. So I do genuinely think that what we have going on here is a firmware bug or firmware issue in this terminal, which is a very strange thing to have. So for now, it looks like everything is working perfectly, ready to go for VCF Southwest, except for the hard drive platter. You can see that disk 1 still shows up as all stars, but we're writing a piece of software to circumvent that, and it's nothing special. We just hop into the memory monitor and run a loop that formats it for us. So I'm not really going to show that on camera, but just know that if it all goes well at VCF Southwest, you'll be able to see this machine in this state with both platters readable, and you'll be able to sit there and play things like Lunar Lander. You can play this game at VCF Southwest on this machine at the dates shown on the screen. I hope you guys come hang out because I think it's going to be pretty epic. I want to thank you all so much for watching, and I hope to see you in the next episode.